Another face perception task by Proverbio et al. From 2006 used these cute little stimuli, these babies. Well, one's cute, the other one's a bit upset. And this looks at the difference in face perception in left and right brain in men and women for perceiving emotion in these cute baby pictures. And instead of just using reaction time or percentage correct, it actually uses brain waves to measure. So there's no responses to be made, we're just measuring what happens in the brain when you show people these stimuli of happy babies or sad babies, and you show them to the left or the right hemisphere. And so what you see are these wiggly brain waves, and at the top we've got what happens with a neutral baby face, and at the bottom we've got what happens with a distressed baby face. And on the left is what happens in the left hemisphere, and on the right is what happens in the right hemisphere. And there's two lines in each of those four graphs. The bolder line, which in all cases is actually showing the bigger response on these brain waves, is that for women. And the fainter dotted line, which in all cases is showing a weaker response, weaker and slightly slower, is that for men. So women are showing stronger brain responses here, both to neutral and emotional baby faces in both the left and the right hemispheres. But as you can see, the spikes are biggest in the right hemisphere for both men and women. So the right hemisphere is responding more strongly to the pictures of these baby faces. So here's an argument suggesting that maybe the right hemisphere is doing more processing of these baby faces, and it's slightly faster as well for both men and women, although we can see that sex effect. And so here is the sex effect represented as a graph. Now this is how fast those brain spikes were in the brain waves. The blue line here is when you were shown a distressed baby face, and the red line is when you were shown the neutral baby face. And the bars surrounding the points show a measure of the accuracy of the average, so it's called the variance. If it's very wide, it means the data's all over the place. If it's very small, it means the data's all gathered around that mean. So you can see that these are quite noisy data. The women are faster than the men. You know that already. By 4 milliseconds. So don't feel too pleased with yourself, ladies. 4 milliseconds is not very much to worry about. If you're dropping a baby, 4 milliseconds is the difference between here and here. Right? They don't travel very far. So the men are going to be just as good at recognising your baby's emotion as you are in practical terms. In fact, what's interesting from this graph is that women are actually faster to notice a distressed baby than they are to pick up the emotion of a neutral baby. So distressed babies seem to matter more to women, whereas the men, they don't care what the baby. It's just a baby. And they're not actually different at recognising babies that are neutral compared to the women. It's the distressed babies that the women are particularly quick at. But here's the important thing about this, for this lecture, no affected hemispheres. This is general, it happens in both hemispheres, not just the right hemisphere. Where could we find a hemisphere effect? Well, there was one bit of the brain wave that did it, that showed an interaction here. Again, overall, the women are faster than the men. At around 154 to 156 milliseconds. So there's a 7 milliseconds advantage in this bit of the brain wave. But it's the men now who are showing the benefit of the right hemisphere. They are faster to do this baby recognition task in the right hemisphere than the left hemisphere. So the women who are faster overall, they're just as fast in the left hemisphere than the right hemisphere. No hemispherical advantage. It's only in the men who aren't as good at the task of discriminating emotion where we see the right hemisphere advantage. So the fact that there's a right hemisphere advantage for them and they're not very good at doing the emotion weakens the argument that it's the right hemisphere that is doing the emotional processing of baby faces. So overall, it doesn't seem that the right hemisphere alone is what is driving your face perception and recognition of emotion in faces. Now, one of the things that was crucial in the Joe video I showed you, and in the setup of all of these tasks, had to do with the way your mind is controlling your body with the left and the right sides of the brain controlling the opposite sides. So here's a little schematic showing motor neurons from the left hemisphere strongly controlling the right hand in this right-handed person. But it's not an all or nothing control. There's still some weak control of the left hemisphere over the left hand. In a normal person, like everybody here, then there will be dominant effects of the two hemispheres on their own hand. And they will drive out the weaker effect of the other hemisphere. And you can still see this in Joe when you'd had the split, his brain split, that his left hand was controlled by the right hemisphere, and the left hemisphere was not interfering with the picture that was being drawn, whether it was a pan or a saw. So now I'm going to get you to do a little task. So I want you to get a piece of paper and hopefully 2 pens or 2 pencils, 2 writing implements, and hold one in each hand. You're all so well prepared, you haven't just brought your iPads, have you? You have got pencils and paper. Right, so what I've got on the computer, on the screen up here now, are 2 shapes. Right, 3 sides of a square around a dot. On the left of the dot, we've got top, left and bottom, and on the right of the dot, we've got top, right and bottom. What I want you to do is just go down the piece of paper as quickly as you can and draw these using both hands at the same time. Okay? Just start at the top of the paper and go down and draw as many as you can. As quickly as you can. This is going to be a long task. Okay? And remember how that felt. Not too hard, was it? Okay, stop doing that now. I'm going to change one of these shapes. So we're going to keep the left-hand shape the same. It's still top, left, and bottom. Whereas the right-hand shape, I'm just moving it through 90 degrees. It's still 3 lines, 2 90-degree angles, except now it's left, bottom, right. Okay, so go down, out, and up. Try and do this one. Straight down the page. Same 2 shapes, one's just rotating. Shouldn't be any different. Or should it?
It works somewhat.
Simultaneously. Can you do it?
Yeah, a little bit.
Just about. Which one's harder to do? So the first task or the second task? I can't hear you.
Second.
Did you say the first? What did you say? The second task. Great. Thank you. So the second task, now it's the same motor actions, really. You know, you've got just to draw vertical and horizontal lines with angles between them. Why is it so hard to do the second one compared to the first? And the answer is to do with the relationship between your body movements and the fact that each hemisphere, although your left hand is controlled by your right hemisphere and your right hand is controlled by your left hemisphere, when you're doing the first task, they're working together. So you move away from your midline, down and towards your midline. So the information that's leaking from your right hemisphere to your right hand is congruent with the instructions the left brain is giving it. And similarly, the information that's leaking into your left hand from your left brain is congruent with the main control from the right brain, going out, down, in. In the second task, though, the instructions are now incongruent, and that's why it gets harder. Your left brain is still, your right brain controlling the left hand is still saying out, down, in, whereas the left brain controlling your right hand is now going down, out, up. So one hand is going to get left down, and you sort of do a diagonal. And then you get down, out, and you do another wobbly diagonal. And then you get in, up, and it goes, ugh. And you try to compensate for that, and it goes all over the place. So it's the incongruency, and this demonstrates that both hemispheres are able to control both sides of our body because we have this strong corpus callosum, and we have the information linking across it. So here is the typical sort of patterns by controls, i.e. people with unsplit brains. Given the first task, they can do it, and the second task. So is that what your pictures look like when you were trying to do the second task? And came up with sort of wobbly C's and U's rather than nice square things. Give this task to someone with their corpus callosum cut, and they can do it. Because they're not getting this leakage across the hemispheres from the weaker hemisphere, if you like, across the corpus callosum from the weaker hemispheres. This demonstrates the way that our hemispheres are working together, and if you put them in conflict, then you get problems. And that can only happen because they communicate.